Hey guys, so let's discuss about logistic regression. In that I have taken diabetes dataset. So this is a diabetes dataset. There are many input parameters like patient ID, pregnancy, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, age, cholesterol, sodium level, heart rate, vitamin D, exercise per week. So these are input variables or also known as feature variables or independent variables. This outcome is output variable or target variable or also known as dependent variable. Now step 1. First we need to import libraries. One is import pandas as PD, so to read data, to convert it into data frame, and for getting head, tail, first 5 rows, last 5 rows, and also for accessing the data from data frame, and to get statistical summary we need pandas, and numpy for mathematical calculation. And in exploratory data analysis, now, in exploratory data analysis, analysis means analyzing the data. We can analyze the data by seeing graphs, based on graphs. So, to plot graphs, we need matplotlib, and for advanced visualization, for good colors and all, we need seaborn. And there are some other libraries like sklearn that we'll import later. Now, first, so this is diabetes dirty dataset. So copy and paste the location here. So from file explorer, so in hod.zip, this is my folder path, data cleaning dataset. This is my diabetes data. So I've copied the location and pasted it here. And this is the diabetes data dirty dataset.csv, name of the file. So our pandas, it will go to the specific location and access our file, convert this CSV, it will read this CSV file and convert it into a data frame, means rows and columns. So now we have received data frame of our diabetes dataset, and this is df.head. Head to get first 5 rows and tail to get last 5 rows by default. And here if you enter 3 or 7 or 9, whatever number, if you enter here 3, then you will get 3 rows. If you enter here 7, you will get 7 rows. And this data is very dirty because see, it has missing numbers, hash symbol. See here, in 139 hash, which is incorrect, and not a number, which is also incorrect. And there are many flaws in this data. And this is df.info, and will give information about the data. So it will tell the data type of each column, like patient ID is object, pregnancy is in64. In this way, it will tell data type, D type or data type of each column. And this one is describe. Describe function, it will give the statistical summary of the data. Describe is used to give the statistical summary, like in pregnancy column, and this will only consider numerical columns and it will ignore categorical columns. In pregnancy, how many rows are there? Total count, mean, average of all values in that pregnancy column, standard deviation, minimum value of that pregnancy column, 25%, 50%, 75% of the data, and maximum value which is in the pregnancy. So the maximum pregnancies are 12. So this is for numerical columns, and this is known as describe or statistical summary. And now I have taken unique values. So I have taken a for loop so that it will iterate each column and it will return unique values. Why unique values? See, these values may be repeated, like 131, it might come 12 to 20 times in this glucose column. And this number of pregnancies, 7 pregnancies, 2 pregnancies, these 2 pregnancies might come 20 to 30 times in this pregnancy column. So I want only unique values from all these columns so that I can understand what values are there exactly. So this is patient ID. Next is pregnancy. So I got unique values. And next is glucose. So I got unique values. In this, from this unique value, I can see hash symbol, and also these numbers are enclosed in single quotes. So it is considered as a string object. So I have to convert these numbers to numeric. Before converting these numbers to numeric, by the way, here there is O, 0, 0, and this is O. This is hash symbol, and these are enclosed in single quotes. So I have to remove these hash symbols and all special symbols, and I have to convert this string to integer. And next, these are unique values of blood pressure, skin thickness, insulin, and there are also missing values here, NaN. One more thing, in outcome, which is output variable, you need, as it is a binary classification, logistic regression is used for binary classification, means only two classes, yes cancer or no cancer, yes diabetes or no diabetes, spam or non-spam, yes or no, true or false. So here, true, it is in the form of 1.0, 1 and yes. False, it is in the form of 0.0, 0 and no. So here it feels that here there are 1, 2, 3, 4, 5, 6, 7, 8. So our model assumes that there are 8 classes because our model don't know that no and false it is same, 0 and no it is same. So your machine learning model it don't know about this. So you have to convert all no's, false to 0, all yes, true, 1.0 and everything to 1, and also it in numeric. Now I'll separate numeric and categorical. So in numeric, I'll take a list, empty list, two empty lists, one is for numerical, one is for categorical. For loop, so that it will iterate each column. Tf of I dot d types, if it is int or float, then it is numerical. So append that column name in this numerical list. Else, then it might be a string. So then it is a string. So append that column name in this categorical list. So in numerical list, you will get all column names. So this is numerical list. Name of this list is numerical. It contains all column names which are numerical numbers. So this list is categorical. So it contains names of all columns which are categorical. And here glucose is also it considered as categorical because as I already said, here unique values in glucose, it is enclosed in the form of string in a single quote. So it is a string. Actually it is an integer, but here as it is in the form of string, so it has taken glucose as categorical. So then what I'll do is I'll convert this glucose into integer and I'll remove this glucose from categorical list and I'll append it in numerical list. So now I'll take df.isNull.sum. It is used to count how many null values are there in each column. Null values means missing values. So patient ID 0 null values, pregnancy 0 missing values, but glucose it has 80 missing values. Insulin has 78 missing values. So you have to fill these missing values with some number. And as I already said, from categorical as glucose it is in the form of string, I removed this glucose from categorical and I have added it in numerical. But still glucose it is in the form of list string only. So I have to convert glucose to number. So remove special symbols from numerical data. So for I in numerical, okay, I'll remove special symbols from glucose and I'll convert it into string, that's fine. But in numerical data also there might be some special symbols. So for I in numerical, so that it will iterate all numerical columns, because I can't see randomly I have seen that there is hash symbol in glucose. O in glucose. That special symbol is there in glucose. In each and every column I can check. So that's why I'll take a for loop of numerical column. If there are special symbols, it will remove. Otherwise, it will ignore. So df of I equal to df of I dot as type of string. So that number it will convert it into string. Nothing. 25. It will enclose 25 is enclosed in single quotes or double quotes. Then it will convert it into string in this way. That str dot replace. So we must use regex function. It's nothing but this symbol. So it is and symbol or conjunction symbol, means here conjunction 0 to 9 dot hyphen. So accept these values. If there are any other values, because as it is a numerical data, you must need 0 to 9 number dot. If there are decimal points, minus, this hyphen is minus if there are negative numbers. So in a numerical data you need these values, but this conjunction it will say that any value except these values, these numbers, any special symbol except these numbers, then you have to replace with empty string and regex equal to true, so that it will convert. Now all your special symbols are removed, and but as you have converted into string, now you have to convert it into numeric. So after converting it into numeric, check numerical values, unique values of numeric columns. Now you can see there will be no hash symbols or any other symbol if there are in numerical column. In glucose also, initially it was string. Now it has converted into integer. Initially I have seen hash symbol, O, alphabet. Now there are no alphabets. Yeah, still missing values are there. I'll remove that. Now I remove special symbols from categorical data. One more thing. Before removing missing values only you have to do these things, like removing special symbols and all, because to remove missing values, mean or median, I'll fill mean or median of that column to the missing value. That only happens for numerical data. If the data is categorical, I'll fill mode to my missing value. But here as it was categorical, what I'll do is, for I in categorical, if there are any missing values, I'll fill with mode. So here with NN and this missing value, it will fill mode, but which is incorrect. So that's why I have to convert it into numeric. Whatever all numerical values are there, I'll remove that special symbols and all, so that it will be easy for me to fill missing values. Now remove special symbols from categorical data. And categorical data also, there might be special symbols like hash or dollar or question mark. So categorical data means alphabets with actually it is string only, so no need to put this. And so A to capital A to capital Z, small a to small z, and 0 to 9, because though this patient ID is categorical, it has numbers. So your categorical data, it also contain numbers, and this is space. So accept these values, because I kept this conjunction symbol. So accept these values. If there are any other special symbol, then replace it with empty string and regex equal to true. So now it will remove all special symbols, and here as it is categorical, I don't convert this into numeric. Okay, so this is categorical, and I have printed unique values. This outcome, that I'll change this afterwards. Now null values, still there are null values are there, because I didn't replace missing value or filled special values to my missing values. Now I'll fill missing values for I numerical, because in missing value, if df of I dot skew greater than 1 or df of I dot skew less than -1, means it is at skewed data. If your column is skewed, then you have to fill that missing value. Fillna is used to fill missing value with median. In your column, it will calculate median of your column, and fillna means it will fill the missing value with median. That happens only if it is skewed data. So if it is skewed data, I have to fill the missing value with median. Else, if it is not skewed data, means it is normally distributed data. So fill with mean. So this filling with median if it is skewed data, filling with mean if it is normally distributed. This happens only for numerical data. Next, for in categorical, fill mode. If it is categorical, then fill the missing value with mode. That's all. So now you tell me, if initially my glucose is considered to be categorical as a string, categorical, but actually it is an integer. So if I did not convert that categorical to integer and by removing those special symbols, it will consider as categorical and it will fill mode for those missing values in glucose. So before filling missing values only, you have to convert if there are any integers in the form of string, like enclosed in single quotes or double quotes, I have to convert it into integer. Before that, I'll remove all special symbols. That all you have to do before filling missing values. Now df.snl.sum, I have no missing values. And plot box plot. Box plot is used to check outliers and also distribution also. So for I numerical, because box plot is used for numerical data only, SNS cbond dot box plot df of I means df of all numerical values, all numerical columns. Title will be the name of that numerical column. Plt dot show, it is used to display the graph. So here for each numerical column, it will plot the box plot. So this line, middle line is 50% data. So 50% is 2.7 or 3 maybe. So 3 pregnancies. So 50% ladies were pregnant 3 times. Below this is 25%. Above this is 75%. 75% is 6 maybe. So 75% of ladies were there who got pregnant 6 times. Not 6 times, sorry, a complete 6 or 6 times or below 6 times. Now this is maximum value. So maximum times a woman got pregnant was 12 times. Minimum times a woman got pregnant is below 0. Minus means miscarriages. And this 0, this O symbol, these are known as outliers. Maybe 7 times miscarriages, which doesn't come under this range, which is far away from this range, then those values are known as outliers. So from this box plot, I can identify outliers clearly. So these are outliers. So now I have to remove outliers from this. And I'll also check skewness. So distribution of the data by using histoplot. So I'll plot histoplot. KDE means this curve line. Okay. And based on this histoplot, I can identify the distribution like 0 to 2.5 pregnancies. So maximum ladies were there who got pregnant 0 to 2.5 times. And there were many pregnant ladies who got pregnant for 2.5 to 5 times. And there are few pregnant ladies who got pregnant 10 to 12 times. So it will give the distribution of data. Based on the distribution of the data, I can identify skewness. So to identify skewness, I will plot histoplot or histogram. And next is illogical outliers. So outliers, what I'll do is, though they are out of the range, I'll just scale the outliers. That is known as standard scaling, that I'll explain later. But there are also illogical outliers. Illogical outliers means like age. Age might be 200 or 300. That is illogical totally. If age group is from 10 to 70, and if you find 80 or 90, that's fine. Those are known as outliers, okay. You'll scale those numbers. But 100 or 200 or 300, Okay, not even 100, 500 or 700, age 700 years or 500 years. It is impossible and it is illogical. Then those numbers I have to remove. So those illogical outliers are known as incorrect values. So those values are incorrect values. So that values I have to remove it. So I'll use IQR method. So I'll find the range of the data, 25% of the data, 75% of the data. Q3 minus Q1 will be IQR, middle interval. That I'll find lower bound minus that bottom value, which is 25% of data. Below that I'll find upper bound means Q3, 75% of the data. Above that is upper bound. So maximum range will be in between lower bound and upper bound. This will be the maximum range. If it is beyond these values, if any number is beyond this upper bound and beyond lower bound, then that number is considered to be illogical. What I'll do is I'll remove those illogical, and removing means those numbers I'll replace it with median. Removing means I'll consider those illogical numbers as missing value because they're incorrect. That incorrect value is considered as I'll consider as missing value. In missing value, what did I do? I filled the value with mean or median. So here also I'll fill the value with median, especially median. Okay. So illogical outliers in pregnancy, blood pressure, skin thickness, and all, they are removed. And if you don't remove incorrect numbers, or incorrect numbers are also known as illogical outliers, then it will affect your model. And plot, because affect the model means in incorrect way, because 700 age group, it is not there, age. And if the temperature is 700 degrees Celsius, it is incorrect. It is impossible also. So I have to remove those. So that's why I have to use remove illogical outliers using IQR method. This IQR is interquartile range. I have to remove it. So that IQR method is compulsory. After removing illogical outliers, I'll plot box plot again. Now outliers are reduced. Now see the range of the outliers and this maximum number are near. So this number is 350, maximum number is 300. But outliers I changed it to 350. So 350 and 300 are near. So at least those numbers, they had come near to the maximum value. So it has come near to the range. See, now there are no outliers, no circle symbols. And next is correlation. It's really interesting. Correlation means relation between two columns. This columns means numerical column. So correlation is used to check relation between two columns only if there are two numerical columns. So first I'll check relation between two input versus input. There are many input columns, right? In that there are many input numerical columns. I'll check relation between two input numerical columns. So like pregnancy versus blood pressure, pregnancy versus skin thickness, blood pressure versus skin thickness, blood pressure versus insulin, input versus input versus input, and all are numerical columns. I'll check relation of that columns, like how pregnancy is related to blood pressure, how pregnancy is related to skin thickness, how blood pressure is related to cholesterol. And now why do I need to check relation between all input variables? Like how one input variable is related to the other input variable. So why do I need to check this relation? The reason is that, see, if two input variables are less related, so there is very less relation between two input variables, then I must take those input variables. If two input variables are highly correlated, means if two input variables are highly related, if one input variable increases, other input also increases. For example, if pregnancy and blood pressure has high relation, actually it is near to 0. This correlation will be in between 0 to 1. Okay, as 0, if it is near to 0, relation is less. Near to 1, relation is more. But as it is related to near to 0, so pregnancy and blood pressure relation is less. So pregnancy and blood pressure both are unique. So both are not influencing with each other. So I need both values. If pregnancy is related to blood pressure, I mean, if more pregnancies, then blood pressure is also increased. Then I can surely say that if more pregnancy means more blood pressure, then I don't need extra blood pressure column. I'll remove blood pressure column. Example, okay? But because if there are many unnecessary columns which are already related to the other variable, then I don't require that variable, then it is unnecessary. If that unnecessary column is there, then it increases computation power. That's why I'll remove that. But here pregnancy is not related to blood pressure. Means I need pregnancy and I also need blood pressure. So I don't remove these two input variables. By the way, correlation, it is in between 0 to 1. If the correlation is 0, means it has no relation. If correlation is 1, it is highly related. If the correlation is in between 0 to 1, it is related. If it is near to 0, it is very less related. If the correlation is near to 1, like 0.9 and 0.9, it is highly related. And here there are signs also, like plus number. So here it is positive number. This is minus, negative number. If it is positive number, correlation is positive, means they are directly proportional. If one number increases, other number also increases. I mean, one input increases, other input parameter also increases. One thing, here relation is less, but if pregnancy increases, blood pressure somewhat increases. Very less. Relation is less, but it is positive. So small increase you can observe if pregnancy is increased. Very small. So less related. If minus is there. For example, for two input columns, if the correlation or relation is minus 0.9, 0.9 is highly related. Okay. Minus 0.9 means inversely proportional. If one input column increases, other input column decreases. In that way it is related. Inversely proportional. Now if correlation is plus 0.9. Plus 0.9 means 0.9, obviously it is highly related. But if it is plus means directly proportional. If one input column increases, other input column also increases. It might be directly proportional or inversely proportional. If directly proportional, highly related, okay. Whether it is less related, okay. But if it is directly proportional, means positive sign. Inversely proportional, inversely related, negative sign. So that is correlation. And same correlation you can also observe by using heat map visually. So this is heat map. So CORR means correlation, annote means annotation, labels, C map is cool warm means color. So from this I can observe. So pregnancy versus pregnancy versus pregnancy, obviously one means highly related. Pregnancy is related to pregnancy itself. Now pregnancy versus blood pressure versus pregnancy is 0.2. 0.2 is near to 0, so very less related. So in this way you can observe heat map. Observe correlation using heat map. Next is unique values in outcome. So outcome, I said that there were many unique values. I have to convert these values to 0 to 1. So here replace yes to 1, no to 0, true to 1, false to 0, 10 to 1, 0 0, 1 0 to 1, 0 0 to 0. So I'll convert all values to 0 and 1. But still 0, it is this 0 and 1, it is in the form of string. My conversion, it is in the form of integer. So I'll convert this to integer to numeric. So I have only two unique values in output column, which is 0 and 1. That's all. Now correlation between input versus output. Okay. Now I have calculated relation between input and input. Now I will see relation between input and output. Input and output means how your input variable is related to output. Now input versus input, relation should be less. Input versus output, relation should be more. So input versus output, relation should be more, because like pregnancy, it should be highly related to the output. Your pregnancy should influence the output. diabetes, your BMI should influence the output. Otherwise, see, if I place here uh, number of cars or house area, SFT of the house as an input in this diabetic data set, does area of the house influence diabetes? No, it does not influence. So area of the house has no relation with the output. So here similarly, here glucose, and here blood pressure is 0.5, 0.6, 0.7. So these are near to 1. So I'll keep those values. And next, though it is near to 0, it's okay to keep, because heart rate, vitamin D, whether you remove or not, it doesn't matter much, because as these are health related values, so though it only causes high computation power, that's all. But especially for health related data, even if it is less related, it's better to keep, because as it is health related data, it might influence very little. Okay, because your input should relate with the output, your input should influence the output. That's why input versus output relation should be high, means near to 1. And crosstab, so correlation is to find relation between two numerical data. Crosstab is to find relation between two categorical data. Between two categorical data, it will find relation. Next, covariance. So covariance is same as correlation, only it will find relation between two numerical columns, but only thing is, in covariance consider only sign, don't consider number, because in correlation it will change the number and it will convert that number into 0 to 1. But in covariance, some numbers might be 8, some numbers might be 1000. So based on 1010, you feel that 1000 is more, so relation is more. It is incorrect. So forget about these big numbers, only consider sign. In covariance, if there is a plus sign, it is directly proportional. If it is minus sign, inversely proportional. Inversely proportional means if one input variable increases, other input column decreases. That's all. So forget about these numbers, consider only plus and minus sign in covariance. And next is duplicates. So your data set might contain duplicates, like one row, it might be one row might be same in other, or in the same data set, one row might be 12 to 15 times. So these are duplicate values, actually this value is repeated. So in that way, I had many duplicate values. I have 15 duplicate values, so I have to remove those values. So drop underscore duplicates, it will remove duplicate values, because I don't need it. Unnecessary computation power. Now split input versus output. Now I am done with data cleaning, data pre-processing. Still small pre-processing part is there, one step is there, two steps are there. But otherwise data cleaning part is done, exploratory data analysis is also done. Now as it is supervised learning, I need to separate input and output. Segregate input and output. So X contains input variables. Input variables means I'll remove output which is outcome. And patient ID I don't need actually. It doesn't patient ID doesn't contribute to the output. So I'll remove this, and output also, output column which is outcome. Then remaining columns are input which is X. Next is output is Y. Y variable contains output column which is outcome, df of outcome. So you have separated X and Y, input and output. Now split the training and testing data. Now in logistic regression, in all algorithms in your supervised learning, so in all columns in your all algorithms in your supervised learning, you must separate data into training and testing. Training data means out of 100% rows, on some 80% of 80 means 80-20 rule I have taken, 80 or 70% of rows will go for training. Remaining 20% or 30% of the rows, it will go for testing. So I'll test the data so that I'll understand whether it is predicting correct or not. So only 20% test size means 80% of the data will be training data. So as 80% of the data is training data, so so in this training data, I'll train the model by only giving this training data, and stratify equal to random state. Okay, random statements, I'll randomly pick values. See, if there are 100 columns, starting 5 rows means starting 5 patients are non-diabetic, 0 0 0 0 0. Remaining 5 rows, next 5 rows are diabetic, 1 1 1 1 1 1. If I give first 5 rows, all rows are 0. It might be, so all rows are 0. So my model trains only zeros, means non-diabetic patients. It won't train diabetic patients, like how parameters changes when the patient is diabetic. So I'll use random state, so there will be no bias. It will take random values and stratify equal to y. So this is also used to prevent bias. Now when I separate training and testing data, in your training data is 80%. 80% of the complete data is training data. In that training data, some patients might be diabetic, some patients are non-diabetic. So some ratio will be there. So there is a ratio of diabetic versus diabetic and non-diabetic. That same ratio will be there in testing data. So for example, in your training data, or means in that 80% data, if diabetic versus non-diabetic is 3:1. 3 for every 3 diabetic patients, 1 non-diabetic patient is there in your training data. So 3:1. Then in your testing data also, in that 20% of data also, the ratio of diabetic and non-diabetic patients must be 3:1. So the ratio must be same. So number of diabetic patients and non-diabetic patients in your training data means the ratio of diabetic and non-diabetic patients in your training data must be same as the ratio of diabetic patients and non-diabetic patients in your testing data. So it will avoid bias. So in your testing data, so that you can easily identify whether it is predicting diabetes perfectly or not, whether it is predicting non-diabetes perfectly or not. Next is sklearn pre-processing import standard scalar. So this is standard scalar. So fit underscore transform. A standard scaling means, see, there are many columns. There are standardization and normalization, two concepts. Normalization means, you see, there are many columns. Say one column, it contains numbers. That numbers might be 3-digit or 4-digit, like 300 to 300, 100 to 1000 range. Now one more column, it has only single digit or 2 digits, like 10, 20, 1, 2, 3, 4. So the range is different. Now your model will feel that in the second column numbers are more, so it will give more importance to that. But it is incorrect, right? Which column is highly influencing, because you have already found correlation. Which input column is highly correlated with the output, for that column it will give more importance. But here, if the numbers are more for a particular column, it will give more importance, but that is incorrect. So I'll change those numbers in such a way that I'll convert those numbers into 0 to 1. So those numbers, it will come in between 0 to 1. I'll scale it as a percentage, 0 to 1. And that is normalization. So each and every column, numerical column, the range will be 0 to 1 only. Not one column 2 digits, another column 7 digits, like that. Next, standard scaling. Standard scaling, it will scale outliers. Outliers, it will come into the range. So here, it will calculate average of the column. You will get some average, and it will change those numbers. In each column, in that particular column, it will change all numbers in such a way that the average of those numbers, it will be 0. And standard deviation will become 1. In that way, it will change the numbers in that column. So here mean base, so this is standard deviation, and in that numbers, if it is greater than the average, it will consider as positive. If it is less than that average, it will consider as negative, and it will change the numbers accordingly, such that if I take mean of those numbers, we'll get 0, standard deviation as 1. For training data, I'll apply that standard scalar, which is standardization, standard scaling. fit underscore transform. Fit means first it will calculate mean and standard deviation, because I need to know, right, mean before only. Then based on that mean, I'll change those numbers in such a way that the after changing those numbers, the mean will be 0 and standard deviation is 1. So initially I need to know mean and standard deviation. So for that I'll use fit. This fit, it will know, it will identify mean and standard deviation of the each column in training data, and it will transform. Transform means changing. It will change those numbers. It will change those numbers in each column such that mean and standard deviation will be 0 and 1 respectively. So fit underscore transform. Fit means it will learn mean and standard deviation. Transform, it will transform the data only for training data. For testing data I don't use fit. Fit means it will learn mean and standard deviation of the training data. In testing data I do not find mean and standard deviation. Otherwise it causes data leakage. So I'll use the same mean and standard deviation which is there in the training data. I'll use that only. So I don't use fit again. I'll just transform the testing data. So now I have standardized the data. So this is known as feature scaling, pre-processing. Next is SQL and/or linear model. Import logistic regression. Now logistic regression. Now I have to call logistic regression in that model. Now what I have to train? I have to train my model. In that what I have to give? I have to give my training data to my model. So if there are 10 questions, 10 question and answers, in that 8 question and answers I will study. Remaining 2 questions, I don't study. I'll write answer without seeing, so that I'll understand whether I have written correct answer or not. So in that only 8 answers I will see, 8 questions I will see answers for those 8 questions. So I'll study only 8 questions. Means I'll train my model, I'll train my brain with those only 8 questions. Those 8 questions are training data. Similarly here also I'll train my model with only training data. Predict the model. Y underscore predict equal to model or predict of X test. So predicting the model. So after training the model, training the data, so you also, when you train your brain with those 8 questions, now you will test your brain by writing an exam. So writing exam is those other 2 questions which you haven't seen answers. For those 2 questions, you will write an exam, right? So you will write answers for those 2 questions. That is testing data. So that's why X test. X is questions, Y is answer. So now I'll have only X, which is questions. Which questions? Testing questions. So X test. I'll predict. This will be YPred. YPred means predicted answers. My predicted answers means my answer sheet. Now this is Y test means key paper. Already answers will be there with sir, with our teacher, which is key paper. So now I'll compare. Now my teacher, our teachers, they will compare our written predicted answers with the original answer key. Our written predicted answer is YPred, original answer key is Y test. So they'll compare both answers and they will evaluate. So I concatenated YPred, predicted answer, and testing answer. Means predicted means your model has predicted, this is a tested answer means actual key. So now I have taken a concatenated is, so 0 0, this is predicted answer, this is actual testing actual value. So it is correct only, but some values might be different. So here also, so in the same example, so when you write answers, those 2 questions, answer might be correct, but some words might be incorrect, some values might be incorrect. So there you lose marks. By that, how teacher will evaluate? By comparing your predicted answers with the actual data. So that is prediction. Now after prediction you will get marks, report card. So then you can understand how many marks you scored, what's your grade, means what's your accuracy, how much accurate how much accurate your brain is in predicting the answer to a question which is given in the exam. So for that, metrics, accuracy score, you will get the accuracy. So 99.5%. So it is 99.5% accurate in predicting diabetes and non-diabetes both. And this only accuracy is not enough, because 99.9 percentage means 99.5 percentage. So your model is 99.5 percentage accurate in predicting both diabetes and non-diabetic. But how much accurate it is in predicting diabetes, how much accurate it is in predicting non-diabetes? So same, I'll give student example. So in total, if you have scored 1000 marks in our intermediate, our total marks are 1000. So in that, if you scored 900 or 920 or 950, so you scored 950, means 95 percentage is your total percentage in your intermediate. Okay, fine. But is that enough? How much percentage you have scored in mathematics? How much percentage you have scored in physics? How much percentage you have scored in chemistry? That I have to know, so that I'll understand if you have scored more marks in chemistry or less marks in physics. So even if you score less marks in physics, but if you score more marks in remaining subject, my total score will be 95 percentage more. So that only total score is not enough. So I also need marks for specific subjects. So here also I need how much accurate it is in predicting diabetes and also non-diabetes. So for that, there will be classification report. Before that, confusion matrix. Confusion matrix I'll write here. It is 130, 0, 169. It is very simple, but it sounds discombobulating. 130, 0, 169. 0, 1. 0, 1. Prediction actual. So this is actual data. 0 means non-diabetic. 1 means diabetic. So 0 is non-diabetic. Actually 130 plus 0. So total 130 non-diabetic are there. Actually 69 plus 170 diabetic patients are there in total. In that, actual non-diabetic, you have predicted 0 means non-diabetic. Okay, correct. This is known as true negative. Why negative? Negative is 0, non-diabetic, and it is true. So 130 patients you have predicted that they are non-diabetic, negative, and it is correct, absolutely correct, because actually 130 patients are only non-diabetic. True negative. This one, you have predicted 0 patients as diabetic. So you have predicted no patient as diabetic in this data. Actually, no. Correct. Only for this 130. So out of this 130 non-diabetic patients, you have predicted 130 non-diabetic patients, complete 130 non-diabetic patients correctly, that they are non-diabetic. You have predicted. Good. Perfect. And now in diabetic, you see, in diabetic 1, okay, this one prediction is 1. 1 means positive that they're diabetic. 0 means 0 and 1 means false, that actually it is positive, but so they are predicted positive, but actually it is negative. So false positive. So this is known as false positive. So true negative is 130, false positive is 0, and here 1, 0. So predicted. So now I'll see class 1 diabetic. Total 70 are there. 69 plus 1, 70. So actually 70 diabetic patients are there. In that actually 70 diabetic patients, you have predicted 1 non-diabetic patient. Predicted. But it is incorrect. Actually it is diabetic, but you have predicted it is non-diabetic. So it is incorrect. So one wrong. So you have predicted one patient wrongly, incorrectly, that though he is diabetic, you have predicted non-diabetic. That is incorrect. So predicted negative, non-diabetic, but actually it is positive, so false. Next, 69. 1, 1. So predicted positive, diabetic, actually they are also positive. It is true. So you have predicted out of 70, 69 patients you have predicted diabetic. So out of 70 actual 70 diabetic patients, you have predicted 69 diabetic patients correct only. Predicted 69 diabetic patients correctly. One patient, though he is diabetic, you have predicted that he is non-diabetic, which is incorrect. So one mistake you have done, that's why it is 99.5% accurate. So now you have understood that your model is 100% perfect in predicting non-diabetic, less perfect in predicting diabetic. Only 1% he did not predict it. He couldn't. Your model couldn't predict that it is diabetic, but it's okay. Only 1%, right? That's fine. But why like that? Because in your data set, 130. Testing data, 130 non-diabetic are there. Only 70 diabetic are there. In your training data also, more non-diabetic, less diabetic data is there. So as in your data while training, this is testing, okay. In your training data also, more non-diabetic, less diabetic data is there. That's why your model has learned how to predict a patient whether he is non-diabetic based on those parameters. Like it has understood what parameters will influence that a patient is non-diabetic more and less for diabetic, because diabetic patients were less actually in our data set. Not truly imbalanced, very imbalanced, moderately imbalanced, not largely imbalanced, it is moderately imbalanced, so that's why it is okay. Next is precision, recall and F1 score. So in classification report you will get precision, recall and F1 score. So I'll write here 0 1 0 1 prediction actual. So it is negative, but it is also negative, true. 1 1. So it is positive, actually it is positive, true. So it is predicted positive, but it is negative, false. Predicted negative, but actually it is positive, false. Here what is precision? This is prediction, okay. What is precision? Precision for class 0 you will predict. Precision for class 1 also it is there. Recall also for class 0 and recall also for class 1. I'll tell what is precision for class 0. Precision for class 0 means non-diabetic patients. So total, so actually how many patients that your model has predicted non-diabetic? How many patients your model has predicted non-diabetes divided by total number of predictions of actual non-diabetes. So prediction of class 0. Class 0 you see. How many you predicted? They are non-diabetic. How many you predicted that they are class 0? And they are actually correct, which is true negative, divided by how many you predicted class 0, which is actually they are class 0 and but it is not class 1. Means complete class 0 prediction. True negative plus false negative. So actually how many you predicted non-diabetic and it is correct. correct prediction of non-diabetic divided by total prediction of non-diabetic. So how many patients your model has predicted that it is non-diabetic? Now precision for class 1. How many patients your model has predicted that it is diabetic divided by total number of predictions of actual diabetic. So here, so 1 true positive. In that, how many patients you have predicted diabetic? In that, how many are correct? Correctly, they are diabetic only. True positive. In that total number of class 1, like how many class 1 you have predicted and there it is correct. True positive. Divided by total class 1 patients. TB plus FP diabetic patients. Next, recall. For class 0. So how many patients you have, how many actual diabetic patients are there? In that, how many actual diabetic patients are there and it is correctly predicted? True negative divided by total actual, how many actual non-diabetic patients are there and you also predicted it is non-diabetic is true negative divided by total actual non-diabetic patients. True negative plus false positive. And recall for class 1, total how many actual diabetic patients are there? In that, how many actual diabetic patients are there who are also predicted as diabetic, correctly predicted as diabetic? True positive divided by total actual class 1 patients, total actual diabetic patients, false negative plus true positive. So this is precision and recall for both class 0 and class 1. Now why do we need this precision and recall? I'll tell you. So I have already said we have to know how well your model is predicting diabetes and how well your model is predicting non-diabetes. That will understand by F1 score. So this precision and recall, we must take harmonic mean of precision and recall. HP is 2 into precision into recall by precision plus recall. Some formula you have to apply and we'll find F1 score for class 0. Again F1 score for class 1. So for class 0 you got 1, for class 1 you got 0.99. Class 0 F1 score is 0, class 0 F1 score is 1, means 100%. So your model is 100% in predicting class 0, non-diabetic. Class 1 F1 score is 0.99, means 99%. So your model is 99% perfect, sure or accurate in predicting class 1, diabetic. So you can see, right, diabetic, one patient it has predicted wrongly, though he is diabetic it said it is non-diabetic. So one patient it couldn't predict properly, so only 99%, so it's good. F1 score for both class 0 and class 1 it is good. So your model is perfect. If F1 score for class 0 is 100%, that it is 100% sure in predicting non-diabetic. But if this class 1 is 0.02 or 0.3 or 0.5, means F1 score, if it is less for class 1, means if it is less in predicting diabetic. If your F1 score is less for class 1 or any of the class, then your model is not 100% sure. I mean, it is not perfect in predicting that particular class. Then your model is not perfect even if your accuracy is more. Like this is maths, this is chemistry. In total you got 99.5%. 0 is maths, 1 is chemistry. 0 means 100%. But 0 means maths, 100%. Chemistry you got 99%. So compared to maths and chemistry it is 99%. Yeah, it is good obviously. But maths you got 100%. So your brain, so for you it is easy for writing maths exam. So for you it is easy but a bit difficult for writing chemistry exam. So in this way you can identify how much probability in predicting diabetes and how much probability in predicting non-diabetes. So it is 100% perfect in predicting non-diabetes, 99% perfect in predicting diabetes. Done. Thank you. So this is logistic regression.